Okay guys, welcome to the fourth lecture of the Lewis structure series, video series, and today we're going to discuss the acid functionality. But before that, I'm going to cover three structures that is necessary before we run into it. The first is NO3 minus. So N is group 5, that's the structure with 3 single reacting atoms. And then there is O negative, one O negative, because there are 3 oxygens and one of them is going to be O negative to make O3 minus. And that O negative goes here. O negative, I could do a double bond with 1 oxygen to satisfy that. That is just like NO2 minus that we've discussed, but we have 1 oxygen crying outside, and the only choice for it, because my nitrogen is already satisfied, is to do a dative bond, okay? And that's the structure of NO3 minus. I'm going to go and do yet another structure, the PO43 minus. Phosphorus is just like nitrogen, group 5. If it's OOO, the formula is PO43 minus. It means out of the 4 oxygens that I have, 3 of them are O negatives. That means I have to take care of these O negatives first. It means I could join them each with one of these single reacting electrons to make phosphorus satisfied and the O negative all satisfied. And then there's 1 oxygen crying outside, and the only choice is to donate the phosphorus line pair to actually accommodate in that 4th oxygen in the structure of phosphate anion. So this is phosphate. Phosphate also, phosphorus oxygen compounds, has also another wide range of other compounds that we will later talk about. They are not as easy as PO4 triple minus to actually draw the Lewis structure. And the Cn negative. Carbon being the central atom, because it has more maximum number of single reacting electrons, we take it as negative, and if it's negative, it's just like the nitrogen. And if I have a nitrogen as well to make Cn negative, the only way we could actually make both of them satisfied is to make a triple bond. All the 3 single reacting electrons in both of them to actually react. And this is a kind of an exceptional case because the negative charge is going to reside on carbon compared to the previous versions, as we have actually devoted the charge to the whole molecule, not residing on the central atom. Okay, so this is cyanide. And now I'm going to talk about the acidity. Now, acidity or acid functionality is a H plus, a proton, okay? And a proton most of the time attaches to O negative to make an OH or hydroxyl functionality, okay? An OH bond, so to speak. And this OH is actually formed by joining an O negative and an H plus. These two joining to get hydroxyl on a compound that has O negative on it. Okay, so those compounds that has O negative in them are called conjugate acid. We'll talk about them later on, as we don't want to go to conjugate acids or really acid-based topics right now. We just want to know how to do Lewis structures of those. So anytime in any compound, in any Lewis structure, you got an O negative, you could add protons to actually make the acid. So if I have nitric acid, HNO3, I could just get this and join it with a proton. That's the structure. And it's not really important where do we put the H plus, but remember this oxygen here has 2 lone pairs in it, okay? One of the lone pair was the one that we actually have it as the O negative sign. So that negative sign is that 2 electrons that are going to be shared with bare nucleus of a hydrogen, that is proton. Actually, proton doesn't have any electron, so when it gets these 2 electrons, it becomes the OH functionality. Okay, so that's the nitric acid. if we have H2CO3, this is called carbonic acid, and it means OH, and if we took this O negative, make another hydrogen, so that is H2CO3. Nitrous acid is HNO2, so if we take this negative and form a hydrogen. Phosphoric acid, H3OPO4. The three negative charges are going to join each by a proton to make phosphoric acid, which is neutral, obviously. The Cn, I'm going to actually add a hydrogen to the negative carbon, making it cyanic acid, my bad. Cyanide is the Cn-, the name for the Cn- anion, which is the conjugate base of the cyanic acid, which is HCN. Hypochlorous acid, it's HClO. And remember, the OHs are always bent. That's the main feature. You could make them bent down or bent up, but you can't make them straight. It can't be linear, okay? Because there are always two lone pairs here that makes this geometry bent rather than linear, okay? The chloride or the colorous acid, chloride is ClO2-, HClO2 is chlorous acid. Chlorate, the ClO3-, and HClO3 is going to be called chloric acid with adding a H, and the perchlorate becomes perchloric acid if you add a hydrogen. Let me just make this a little bit more clear here. Hydrogen. The sulfuric acid, H2SO4, are going to be joined by getting the two negative charges on the SO4 double minus or the sulfate anion and joining them by hydrogens to make H2SO4. And the sulfurous acid, it's going to get the same two negative oxygens, joining them by the hydrogen to make OH. Now I hope you could see that one below. Yes, we could see that. And that is the story of the acids, okay? Or you could simply also say, without the bond, just write OH here, okay? So OH is the hydroxyl and it's the acidic functionality, okay? With that, I want to move on to another class of Lewis structures, those that have a diatomic central part. Like the ones that we have so far talked about are those that have one central atom. Now I'm going to move on to some examples that have two atoms in their as their central moiety, okay? And if there are two atoms that say central moiety, you're going to see that in their formula right away, okay? Let's start with a simple one, okay? Let's start with the C2O4 double minus. That's oxalate. So C2O4 double minus, and there's a rule for this, and the rule says if I ever told you about the central moiety, you could see that there's a C2, and if I told you about it, you had the privilege of knowing a little bit info about this. If not, if you're not given any information by the problem itself about the central moiety, it means you have to do X single bonded to X and start from that. So this is the case for oxalate. We don't have any extra information. If I'm going to ask you about the Lewis structure of oxalate, and you're going to say, okay, that's my starting point. The central moiety is actually joined together, the two carbons, by one single bond. So that's going to be 3 singles electron each. Why? Because the first one is actually, we know carbon has 4 single reacting electrons around it, and the first one is actually used up by that central bond between. So O4, 2 of them minus to make the double minus. So that's O4 double minus here. And we're going to take care for the O negatives first. So I just do join one of them with this single reacting electrons and join another with another single reacting electrons to make it symmetric on both sides, okay? And that's most of the time, 99% of the time, the case. The O's that are remaining, each O is group 6. Each O has 2 single reacting electrons, and on each carbon I have just the exact amount of 2 single reacting electrons, so I could make a double bond between one of the oxygens and another double bond between the other to satisfy not only both of the carbons but also both of the oxygens. So that's the structure. There's no name for the Lewis structures with 2 atoms in the center, but there is a rule that I want you to actually consider when you're drawing it, okay? And that rule is to actually consider the number of lone pairs around us and surrounding atoms, okay? So it's 3 surrounding atoms, no lone pair. It's going to be this structure, trigonal bipyramidal, and also here the same exact thing, okay? So that's going to be the same exact idea. Just grab my models down from here, and I could show you that there is this one and this one. So the only way that I could draw this is to join up 2 trigonal planar moieties. I can draw it only and only like this if 2 of these structures are going to join together to form that oxide. Any other form, if you do something like this, for example, would be wrong, okay? Something like this is going to be wrong because it doesn't have the maximum repulsion between the bonds. You remember, these frameworks, the trigonal planar framework that we talk about, is important because the shape of the molecule. Now, there's no name for it, but you have to draw it like this, okay? So that's going to be this framework. Again, you don't have to do the green boundary around it, but it has to be just like this skeletal form, not something like this, not any other acceptable forms. Okay, just 2 of this connected together. Let's now talk about another example. There is a series of nitrogen oxides. Remember when we talked about the nitrogen, I told you the nitrogen molecule itself. I told you it's a triple bond between the 2 nitrogen and it's hard to break. When we have a series of nitrogen oxides, I'm going to write their name down here real quick. N2O, N2O3, N2O4, and N2O5. These are the ones that I'm going to talk about, the user structure of. But before doing so, I'm going to actually let you know a trick, or it's not a trick, but there's a pattern that you could rationalize somehow how these Lewis structures are going to work. Now in the test, if I'm asking about this or ask you about this, I'm going to give you exactly what you're going to start with, okay? But in these 2 cases, I'll just leave you like I did with oxalate, so you know that there is N single bond N that you're going to start with. For this one, it's going to be this one that I'm going to give you. This is the structure of the central moiety, and for this one, I just gave you this, or I told you that it started with N2 molecule itself. And it's interesting, as the number of the oxygen increases, you could see that the bonds between the nitrogen actually decreases, okay? So there's 3 bonds between the 2 nitrogen, 1 bond between with O3O and O4, and if there are 5 oxygen, there's actually no real bond between the 2 nitrogens, okay? So the number of bonds between the 2 nitrogens are going to decrease as the number of my oxygen increases. That's the pattern that I wanted to talk. So let's start with this one. That is one of those cases that I gave you the central moiety because it's not just a single bond between them. Other cases, when I don't talk, it's going to be X connected by X, just as oxalate and video, and just like these two that we're going to do. So this is the structure that I'm going to start, and there's one oxygen outside. My oxygen is already feeling satisfied. Each nitrogen is group 5. It has 3 single reacting electrons shared with the other one. They both feel satisfied, so there's no choice for me to actually donate this lone pair. Now on this one, which becomes central atom, now some of the students ask me, could we take this one? Yes, that one becomes the central atom. There's nothing wrong with that one if you do that, okay? But there's only one oxygen, so the oxygen could be here or here. That doesn't really make your case any different. So you have 0 lone pair, you have 2 surrounding atoms, and that's the linear geometry. That's the geometry of your molecule user structure, okay? So that's how you draw this. Let's go to the case of N2O3. Now N2O3, I told you it's going to be like this. Nitrogen has 3 single reacting electrons and 1 lone pair each. The third single reacting electrons, it's not being shown here because it's in the bond between them. And if I don't give you any instruction on the case, which is the case for N2O3, and also will be the case for N2O4, this structure would actually be the two atoms in the diatomic moiety or the diatomic center being connected together with just one single covalent bond, okay? For the 3 oxygens that I have, I could get one of those oxygens and satisfy it like this. So oxygen is group 6. If I join the 2 single reacting electrons on my oxygen with the 2 remaining on my nitrogen, I could connect them together with simple covalent bonds to not only satisfy my oxygen, but would also satisfy this nitrogen. And the same story could also happen with this guy as well. The 2 single reacting electrons on my oxygen with the 2 single reacting electrons remained on my nitrogen to get my oxygen, the second oxygen and nitrogen also satisfied. Now remember, you have 3 oxygens, so there's 1 oxygen left outside, and if you want to take care of that, we just have to take either this one or this one. I'm going to take this one and make a dative bonding to it. Now remember, just like the case of oxalate that we just did, and it was this framework, here we have the same exact story. On this nitrogen, I have 0 lone pairs, I have 3 surrounding atoms, this one, this one, this one surrounding this nitrogen, and on this one I have just 1 lone pair, and 1 and 2 around this nitrogen, 2 surrounding atoms. So both of them gave me 3. This structure, or sort of this framework. For this one that is no lone pair, just 3 surrounding atoms, there is this trigonal planar, which is this one. So your structure on this nitrogen should be trigonal planar, and on this one there is also this framework with 1 lone pair, so it should be bent. So this one, because you know, trigonal planar with just 1 lone pair should be a bent structure. So your structure could be this. It could also be this framework if you like to, like a trigonal planar on this side, and this one goes up. That doesn't really change anything, okay? So trigonal planar on this side, and this one, actually, it could go up or down, doesn't really change any story, but it could not be linear or it could not be 90 degrees, okay? So any of those 2 structures I would got that as a wrong answer, okay? This one should always be bent because it's a trigonal pyramidal framework, a trigonal planar framework with 1 lone pair, okay? So I detach one, it could go up or down, but it can't be linear or 90 degrees. So that's the N2O3. Let's talk about N2O4, which is very similar to oxalate. That is the exact same story that we started with N2O4, N2O3, my bad. And the only difference is that we have now 4 oxygens. So the first oxygen, I'm going to get a double bond satisfied. The second oxygen, I'm going to get the double bond satisfied. Now my whole whole structure has been satisfied. Now for the dative bond, we talked about dative bonds previous session, and we told you that we could actually go through dative bonding when we have the central part of, or the molecule half drawn being all the atoms satisfied. This oxygen satisfied, this oxygen satisfied, and my central atoms are all both satisfied. So there are two choices. One of them was dative bond. On the next lecture, we're going to talk about the other choice, which is hyperactivation. So if I just donate this one to the oxygen, that would host in the third oxygen, and if I donate this one, that would host in the fourth oxygen. This is going to be a trigonal planar joined together by another trigonal planar structure, just like oxalate. Okay, so I don't have two of these moieties. There is no name for the Lewis structure that has two central moieties. So there's this one and there's this one. You could see that if I join two of them, I would have this geometry. There's no name for the geometry. The only thing that I know is that my geometry is going to be planar. It's one of these here and the other one just like this here. So it's in a plane. That's N2O4. Let's talk about N2O5. And N2O5, I have to give you extra information. And the pattern works here because we started with N2O, where we have 3 bonds between the nitrogen, then the number of the bonds between the nitrogen decreases as we actually increase the number of oxygens. So N2O3 and N2O4 both have structures where you have one bond between the two nitrogens, and also this one that has no bond between the two. So there's the central moiety. It's kind of a bent configuration. It's interesting because the two nitrogens are actually joined in an oxygen that has 2 lone pairs and 2 bonds here. So it's kind of like water, just rotated upward. That's what I'm going to give you, even in a test. And that's what you're left with. Okay, that's the central moiety. I have 5 oxygens. Here I have already included one of them, and there's 4 that I could actually hoist in this structure. Again, there is no shape, total shape for the molecule. As I satisfy my third oxygen and my first oxygen with the remaining single reacting electrons, there are 2 on each nitrogen, and on my oxygens, because they're group 6, they contain 2 single reacting electrons, so I could make 2 double bonds, and that is the structure so far. And there are 2 other oxygens to make an N2O5. Okay, and I'm going to do this. They leave bonding on both of them to actually do N2O5. And now you could see that there is 2 of these trigonal planar structures, one here, and they're connected with sort of a bent structure, something like this. If I get a tetrahedral and attach 2 for the central oxygen here, 2 lone pairs and 4 surrounding, actually on a tetrahedral, 2 lone pairs, I have to detach these 2 for the lone pairs, and that's a bent structure. So you could see this is joined with this, and also there is another one joined with this. Okay, so that's the story for this molecule, the N2O5 structure. I'm also going to talk about one final example before I finish, and that's going to be another diatomic central molecule with S2O7, my bad, double minus. Okay, and for this I'm going to tell you, okay, that is just like the nitrogen that you have SOS. Okay, so that's the exact same story. I'm going to draw the central moiety. Now for sulfur, there are 2 lone pairs and 2 single reacting electrons. The second single reacting electrons on each sulfur is being connected to the central oxygen, and there is only 1 single reacting electrons remained on each one. 1 oxygen has already been used up, so there is O6 2 minus that remains. It means there are 6 oxygens now. 2, 4, 6. 2 of them are negative. And one of the oxygens which is not negative is this one, to make O7 double minus. Okay, so I do O minus here, O minus here. O minus again is just like fluorine, so just 1 bond is going to satisfy its hunger for electrons. So that's the structure for the O minuses. I took care of my O minuses, and there are 4 oxygens remaining, and my structure fills octet. You know, all of these that you could see, group 7, 1 bond, group 7, bond, group 6, group 6, group 6, each of them 2 bonds, so all is satisfied. The only choice that I'm left with is to donate the teeth bonds, and my sulfurs has plenty of those, how to say, of those lone pairs, okay? So I do donate 2 of them. Let's just get rid of these 4, and I'm just trying to put them in correct order. And you could see that now I have 2 tetrahedral frameworks. On both sulfurs I have 0 lone pair plus 4 surrounding atoms, 1, 2, 3, 4 around this, and 1, 2, 3, 4 around this. Just get rid of this central moiety on the top. That's tetrahedral framework. So 2 tetrahedral frameworks joined with an oxygen through the center. Okay, so that's what you have. Okay, so this is what we have. Again, we have this tetrahedral framework and another tetrahedral framework joined by an oxygen that is also a bent structure. So there's again no name, but the structure should look like this. Okay, it doesn't really matter where the oxygen negatives are. Oxygen negatives could be this one, and also here it could be this one or that one. That doesn't really change anything, but the whole form and the whole shape could be like this. Okay, so I hope you enjoyed the video. It's getting a little bit lengthier. There is going to be one final video that I'm going to post, and that's hyperactivated bonds. And with that, we will like to finish these structures.